Free energy. Gibbs free energy is a measure of spontaneity. Spontaneity depends upon the dispersal of energy. Losing energy from a system will favor spontaneity. Decreasing the order of the system, in other words, creating more possibilities, will also favor spontaneity. In a situation where we have an exothermic reaction, where the system is releasing energy with a negative enthalpy, but we have a process by which it's becoming more ordered. So for instance, something like the freezing of water, where it's releasing energy but becoming more ordered, so disorder is reduced, and a negative entropy, so we have both negative enthalpy and negative entropy. Some of the energy that is released from the system has to be used to increase the system's order. This reduces the overall energy that is free to do work. If I have a positive entropy, on the other hand, rather than a negative one, where I'm producing more disorder, more energy is released to do work than just the energy that comes from the enthalpy sign. The relationship between the energy released from the enthalpy term and the energy released from the entropy term is referred to as free energy, or the energy that is available to do work usefully. This was formulated by J. Willard Gibbs and is a specific equation used to relate entropy and enthalpy together. We can calculate free energy from the entropy and enthalpy terms of a system. We know that the overall entropy of the universe is equal to the entropy of the system plus the entropy of its surroundings. The entropy of the surroundings is equal to the energy released by the system, in other words, the negative enthalpy of the system divided by the temperature, because entropy is a temperature-dependent process. The overall entropy of the universe can then be viewed as being equal to the entropy of the system minus the enthalpy of the system divided by temperature, because we can substitute the negative delta H system over temperature in for delta S naught surroundings. If we multiply the whole equation by negative T, this becomes negative T times the entropy of the universe is equal to negative T times the entropy of the system plus the enthalpy of the system. Negative T times the entropy of the universe is defined as Gibbs free energy, abbreviated delta G. The equation then becomes delta G is equal to negative T delta S of the system plus delta H of the system, or rearranging this, delta G is the entropy of the enthalpy of the system delta H cis minus the entropy change of the system T delta S cis. The magnitude of the decrease in the Gibbs free energy is equal to the energy that is released from the system available to do useful work. In order for a process to be spontaneous, the process must lose useful energy to the universe. An overall increase in useful energy means that energy has to be put into the system. This would be a non-spontaneous reaction because the energy is drawn from the universe, which is not something that normally happens. The more negative the enthalpy and the more positive the entropy, in other words, the higher the loss in energy of the system, the more spontaneous the reaction is going to be. So positive entropy will favor spontaneity. A negative entropy will disfavor spontaneity, because a negative entropy will reflect an increase in order rather than a decrease in order. A negative enthalpy will favor spontaneity because it reflects a loss of energy, but a positive enthalpy will disfavor spontaneity because it reflects an absorption of energy. A process where both the entropy and enthalpy terms are favorable will always be spontaneous. In a situation where both the entropy and enthalpy terms are disfavored, the process will be non-spontaneous. In most cases, one of the terms, entropy or enthalpy, is favored while the other is disfavored. These reactions are temperature dependent. Overall, the sign of delta G reflects spontaneity. A negative delta G will be spontaneous. A positive delta G will be non-spontaneous. A value of 0 for delta G reflects no change in the overall energy of the system, which means that the system is currently at equilibrium. The value of delta G depends upon state, thus it is subjected to both pressure and temperature changes. We can compute the delta G of the reaction as it is a state function. Delta G being a state function can use standard reference points. 298 Kelvin in 1 atmosphere is standard state. For an element, the free energy of the reaction is 0, just like it is for enthalpy. We can use standard values of reactants and products in the same way with Hess's law that we have done with enthalpy and entropy in the past, where the overall free energy of the reaction will be equal to the sum of the coefficient times the free energy of the products minus the sum of the coefficients times the free energy of the reactants, all at 1 atmosphere in pressure and 298 in Kelvin. The value of the delta G of the reaction allows us to compute what we call a standard reaction, or the reaction at standard state. This reflects a complete conversion of 1 mole of reaction of the reactants to 1 mole reaction of products, in which all the reactants and all the products are at standard condition. As an example, is this reaction spontaneous if I have the combination of nitrogen and oxygen to produce nitrogen monoxide? The overall free energy change are 0, 0, and positive 86.57. To plug this in, the delta G of the reaction then would be 2 times the delta G of the nitrogen monoxide minus a combination of the delta G of the oxygen and the delta G of the nitrogen. If I put in the numeric values, 2 times 86.57 minus 0 plus 0 is positive 173.1 kilojoules per mole. Because delta G is positive, the reaction is non-spontaneous at standard conditions. Most reactions do not occur at standard state. Most reactions occur at some different temperature or even different pressure. Thus, it is the delta G of the reaction, not the delta G naught of the reaction, that is important. However, we can also get an equilibrium mixture. At an equilibrium mixture, this reflects a system that is more stable than a complete product or reactant conversion. So most systems will not go all the way to product or all the way back to reactant under any conditions, because usually the most stable configuration will be some form of equilibrium. We can calculate delta G from the change in entropy and change in enthalpy. This occurs under constant temperature and pressure conditions. If we plug in our equation where delta G is equal to the entropy of enthalpy of the system minus T times the entropy of the system, this technically reflects products and reactants at standard state. However, we can use it to estimate the reaction for any particular temperature from the standard reaction. Since temperature is always in Kelvin, and enthalpy is in kilojoules per mole, and entropy is in joules per mole Kelvin, we must convert whatever units we're given into proper units. Is the following reaction spontaneous? If I take nitrogen and oxygen and combine them to make nitrogen monoxide, the reaction we just looked at. Its delta H is 0 for the elements and 90.25 for nitrogen monoxide. The S values are 191.5 for nitrogen, 205 for oxygen, and 210.7 for nitrogen monoxide. The delta H of the reaction then is 2 times 90.25 minus 0 plus 0, or 180.5 kilojoules per mole. The delta S of the reaction is 2 times 210.7 minus 191.5 plus 205, or 24.9 joules per mole Kelvin. This is also 0.0249 kilojoules per mole Kelvin. The delta G then is the enthalpy of 180.5 kilojoules per mole minus the temperature of 298 Kelvin times the entropy change of 0.0249 kilojoules per mole Kelvin, or a positive 173.1 kilojoules per mole reaction. That is what we calculated from the free energies of the products and reactants previously. Now, spontaneity is temperature dependent. We can estimate the temperature at which a process achieves equilibrium, for instance. This occurs when the delta G of the reaction is 0. The delta G of the reaction is 0 when the delta H of the reaction is equal to T times the delta S of the reaction. In other words, then, the temperature of this equilibrium process is the enthalpy, delta H of the reaction, divided by the entropy, delta S of the reaction. What is the normal boiling point of hydrogen peroxide? If the reaction from the hydrogen peroxide liquid to the hydrogen peroxide gas has negative 187.6 kilojoules per mole for liquid, negative 136.1 kilojoules per mole for gas for the enthalpy, and 109.6 and 232.9 joules per mole Kelvin for the entropies, our change in enthalpy is negative 136.1 minus negative 187.6, or a positive 51.5 kilojoules per mole. our delta S is 232.9 joules per mole Kelvin minus 109.6 joules per mole Kelvin, or 121.3 joules per mole Kelvin, or 0.1213 kilojoules. Plugging it into our equation, 51.5 divided by 0.1213 is 424.6 Kelvin, or 151.4 degrees Celsius. The actual boiling point is 150.2, so a very close estimation. There are 4 possible configurations for entropy and enthalpy combinations. If the delta H is negative, favorable, and the delta S is positive, favorable, the reaction will always be product favored. If the enthalpy is favorable and the entropy is disfavorable, the product will be favorable at low temperature. If the enthalpy is disfavorable and the entropy is favorable, the product will be favorable at high temperature. And if the enthalpy is disfavorable and the entropy is disfavorable, the reaction will always be reactant favored. Thus we see that opposite signs of enthalpy and entropy work in the same direction, either spontaneous or non-spontaneous. These are temperature-independent reactions. If they have the same sign, they'll compete against each other, and in these cases, the reaction becomes temperature-dependent. Delta G equals 0, the equilibrium point, is the spontaneity limit. The sign of the entropy then shows whether or not the reaction is spontaneous above or below the temperature of equilibrium. As an example, estimate the temperature range where delta G reaction is product favored. For the reaction here of HGS plus O2 going to Hg plus SO2, we can calculate our enthalpy change from the enthalpies of the products, negative 296.8 plus 0, minus the enthalpy of the reactant, negative 58.2 plus 0, which gives us negative 238.6 kilojoules per mole. We can calculate our entropy change from the entropy of the product, 76.02 joules per mole Kelvin, plus 248.1 joules per mole Kelvin, minus 205 joules per mole Kelvin plus 82.4 joules per mole Kelvin, or 36.7 joules per mole Kelvin. In this case, entropy is positive and enthalpy is negative. Both of these are favorable, which means that the reaction will always be spontaneous, and thus will always be product favored, regardless of temperature.